Hello guys, welcome to Noble Mind Science Tools Online. This is your online video tutorial of online physics class, and I'm Otobo Michael. I'm your online physics instructor. So today we'll be looking at electromagnetic induction. Electromagnetic induction. We have discussed electromagnetic field and we've seen the applications of electromagnetic field. So today we're going to look at electromagnetic induction. You know, in our previous class, earlier, like we discussed electrostatic induction. Okay, if you can recall back, we've discussed electrostatic induction. So this one, we're going to discuss electromagnetic induction. So guys, if you have not subscribed to our channel, please, what are you waiting for? Subscribe now, so that when we upload a new video, YouTube will always notify you. Then you will have access to our complete playlist, play videos. We have treated a lot of topics in physics. We're almost rounding off now, so just subscribe, click on the notification bell so that when we upload the video, YouTube will notify you. We're also working on other subjects. Very soon we'll start to upload all those ones, like chemistry. So please subscribe to our channel and give us a like, give us a thumbs up. If you have any challenge, reach us through the WhatsApp number that's showing on your screen or through the WhatsApp link that is down below. Okay, give us a thumbs up and a positive comment, and also help us to share this video in your various social media platforms. Right, so get your writing materials ready so that we can discuss our topic for today, electromagnetic induction. You are welcome. Okay, so a an earlier scientist actually carried out an experiment on electricity, and he made a discovery that was very timely and important, and that is discovery what we are discussing today, electromagnetic induction. And that scientist is called Michael Faraday. Okay, so far you will discover that Michael Faraday did a lot of work on electricity. In fact, he's the father of electricity. Alright, so Michael Faraday made the great discovery that an electric current can be produced in a conductor under the influence of a varying magnetic field. So what that means is electromagnetic induction is the production of voltage or electric current in a conductor. Whenever there is a relative motion between the conductor and the magnetic field or magnets. Alright, so when a solenoid is connected to a galvanometer as shown below, okay, so this is a solenoid. Alright, we've seen this before. This is a picture of a solenoid, and then so assuming this is a solenoid and it is connected to a galvanometer. Okay, so this is setup. Now if the north pole of a strong magnet is moved towards the solenoid, the galvanometer will deflate for a short time to the right. This deflection shows that there's an induced current or voltage on this particular coil. Now, if the south pole of the magnet is moved towards the coil, the galvanometer will deflect to the left. Then when the magnet is kept stationary, if it is not moving, if it is kept in the coil, no deflection is observed. No deflection is observed. Okay, so this is an observation that Faraday had, and what that simply means is that there is an induced current when a magnet is moved close to a coil or close to a solenoid, and that current is what is detected by the galvanometer. Okay, that is the current that is detected by the galvanometer. Now, the induced EMF or current, one, depends on the speed of motion of the magnet or the coil, the number of turns of the coil, the presence of a soft iron core inside the coil. So these are the factors that the induced current or EMF depend. One, the speed at which this magnet is brought towards the coil. Then the number of turns. Then the presence of a soft ion on this solenoid. Those are the factors that the induced EMF or current depends on. So when you are talking about current by induction, the magnet is not touching the solenoid before you observe it. Once the magnet is brought, don't forget that in a magnet there's magnetic field in the magnet. So when you bring the magnet close to the solenoid, the galvanometer will show that yes, a current or an EMF has been induced on this particular solenoid. Alright, so this is the phenomena and this is the observation that is described as electromagnetic induction. So electromagnetic induction is production of voltage or electric current in a conductor when there is a relative motion between the conductor and magnetic field or magnets. So if you are asked this kind of question, you should be able to draw this and use this to indicate the direction of this thing, right? Just be able to draw this drawing, or you can draw any of this and use to describe. If you can draw this picture and you are able to write a little about it, you have your full mark in physics. Alright, so the induced EMF or current depends. The induced EMF on this depends on the speed of motion of the magnet, the number of turns, and then the presence of a soft iron core. Alright. So the induced EMF. An induced EMF is produced in a straight conductor when the conductor moves across a line of force of a uniform magnetic field. Alright, so in that instance, the conductor is the core, is the solenoid. Okay, so if the solenoid moves in a magnetic field, if it moves across a magnetic field, an induced current is produced. The direction of the induced EMF in a straight conductor is given by Fleming's right-hand rule. Don't forget we discussed Fleming's left-hand rule. In this one now, we are talking about Fleming's right-hand rule. When we talk about electromagnetic induction, electromagnetic field, we mentioned Fleming's left-hand rule, but this time we are talking about Fleming's right-hand rule. The Fleming's right-hand rule states that if the thumb, the forefinger and middle finger of the right hand are held mutually at right angle to each other, with the forefinger pointing the direction of the field and the thumb pointing direction of motion, then the direction of current will be indicated by the middle finger. So the direction of the EMF and the current will be indicated by the what? The middle finger, and that is it. Okay, so you see that in Fleming's left hand we are talking about the direction of motion, but this time we are looking at direction of current. Okay, so the induced EMF is maximum when the conductor moves at right angle to the lines of the magnetic field. It is zero when the conductor moves parallel to the field. It is the same thing that we discussed when we talked about electromagnetic field. So when the conductor moves at right angle to the magnetic field, the induced EMF is maximum, and induced EMF is given by this, where B is magnetic flux, L is length of conductor, and V is velocity of motion. Okay, So please take note of this equation and then take note of the Fleming's right hand rule. Okay, so now we're looking at the laws of electromagnetic induction. There are two basic laws that governs electromagnetic induction. One is Faraday's law and the second one is Lenz's law. Faraday's law states that whenever there is a change in the magnetic lines of force, an EMF is induced, the strength of which is proportional to the rate of change of the flux linked with the circuit. What this simply means is what we have discussed. When a conductor is brought or moves in a magnetic field, an EMF is induced. Is that okay? So that is when a conductor moves in a magnetic field, an EMF is induced. The strength of the induced EMF is proportional to the rate or to the speed at which the conductor moves in the magnetic field. So that is what is stated here, proportional to the rate of change of the flux linked with the circuit, the same thing. So the magnetic flux linking the circuit depends on the magnetic strength of the magnetic field strength, same thing we have discussed before, the number of turns of the coil, we've discussed this, the area of each turn, which is the area of the coil, the area of the coil. Okay, so Faraday law gives the magnitude of the induced EMF. So to obtain a large EMF, a coil of many turns moving with high speed across the magnetic field is what used. Alright, so please, I hope you are following. Please, I hope you are following. Go through this lecture gradually. You will understand it. What you need to do is just try to picture the electric motor. If you can understand the electric motor, how it works, you begin to translate that knowledge upwards up to this point. You will understand what I'm discussing gradually. Alright, so please go through this video gradually and try to understand. You find that all we have mentioned there, they are the same thing we have been mentioning since. Magnetic field strength, number of turns of the coil, the area of each turn, use of soft iron core, all of them, they are just the same thing. They are just using different way of twisting the grammar. But there's no grammar twist here. Just understand it that whenever there is a change in magnetic, what that means that when you bring a conductor into a magnetic field, there's an induced EMF. The strength of the induced EMF depends on the rate at which you bring that conductor to the magnetic field, and you can increase that strength by increasing the magnetic field strength, the number of turns, and the area of each turn. Or every other thing is grammar. Is that okay? Understand it that way. All right. So the next law is Lenz's law. Okay, Lenz's law. This second law of electromagnetic induction. This law states that the induced EMF, that is when you bring a magnet close to a conductor, the induced EMF is such, the induced EMF is in such a direction as to oppose the motion or change producing it. Plenty grammar, right? Okay, what this law is telling you that when you bring this magnet close to the conductor, you know, we have said that there will be an induced EMF, right? So the induced EMF, they say it's in a direction so as to oppose the motion. You know that when you are, like, assuming you bring a north pole to the conductor, that is to the solenoid, the end that is close to the magnet on the solenoid, we experience a north pole too. So if a north pole is on the side that is close to the magnet on the solenoid, and you are bringing in, and you brought a north pole magnet to the solenoid, what naturally will happen? There will be repulsion because you have two like poles, right? So there will be repulsion. It means that there will be repulsion. So it means that the magnet
will be pushed. There will be a force that will be opposed. As you are bringing the magnet close, you see that there's a force that is trying to push your hand backward. That is what Lenz's law is saying. It acts in such a way as to oppose the motion. You are bringing in the magnet close and it is pushing your hand backward. It acts in such a way as to oppose the motion or change producing it. So it's trying to push your hand backward. You are pushing your hand in. So which means that you now have to exert more force for you to push the magnet to the solenoid. That force you are pushing in, you are exerting, is a mechanical energy that you are putting in, you are producing. You are now doing work. You are doing mechanical work to push the magnet as it is opposing. You are pushing it so that it can get close to the solenoid. So a mechanical work is being done. And mechanical work is what? Force times what? Distance. I hope you understand that. So that is all the explanation that is here, that when the north pole of a magnet is moved toward the coil whose end is joined to a galvanometer as shown here, a current is induced on the coil. Now the face of the coil that is close to the magnet will acquire a north polarity as shown in this particular picture. This north polarity, you see, because it has a north polarity, the current that will flow here will be in the anti-clockwise direction. Okay, this non-polarity will oppose the movement of the magnet by repulsion of like poles, as that's what I've discussed before. Hence, the current in the coil will flow in anti-clockwise direction. See the current flowing. These are the drawing that you need to take note of in your examinations. They can give you the drawing and change the direction of the current. You will not even know. There will be a non-pole here. The direction of this current will come down. It's wrong. So here, north pole, direction of current is anti-clockwise. Do you understand that? So now, if you are now, like I said before, you have a north pole and north pole, there's repulsion. So that is one part of the Lenz's law. Now another part of it is that if you want to now remove the magnet, what will now happen? On the coil, a south pole will now be produced on the end that is close to the magnet that you are pulling out, that has a north pole close before. A south pole will now be produced. Now if there's a south pole produced and it's trying to pull the magnet, what will now happen? These are unlike poles, attraction will now come. And that is what Lenz's law is talking about. There's always an opposition force trying to oppose it. So as you are trying to pull the magnet away, the attraction force is pushing your hand back. So work will not be done. You will not do work. A mechanical work has to now be done for you to be able to separate the magnet from the coil. That is what Lenz's law is also always talking about. So if you are able to even understand that, you can explain Lenz's law freely. Even if you are sleeping and somebody will can say, what do you understand by Lenz's law? You should be able to explain it. That the induced EMF acts in such a way as to oppose the motion that is producing it. Then you draw this drawing and then not attraction, not repulsion, opposing your motion of bringing in, then not sat attraction, opposing your motion of removing the magnet. That is just it. So mechanical work is done in moving the magnet against the force of repulsion and attraction from the coil. And so energy is transformed to electrical energy in the coil. So if the north pole of the magnet moves away from the coil, as shown in this place, the face of the coil will acquire a south polarity to oppose this motion by the attraction of unlike poles, as we have discussed. Current in the coil will therefore flow in the clockwise direction. Look at it here. Look at it here. Yeah, I hope you are seeing it. I brought this one too so that it will be clearer for you to see. Alright, so the mechanical work done in moving the magnet against the force of repulsion and attraction from the coil is transformed to electrical energy. The mechanical work done is transformed to electrical energy in the coil. So Lenz's law is an example of energy conservation principle. Alright, Lenz's law is an example of energy conservation principle. So it is good that you understand this aspect of electromagnetic induction. Okay, it is very, very important, and this is the principle that drives most of your dynamos. Yes, your dynamo that converts uh, mechanical energy to electrical energy, right? Like you have your generator, the generator that you use at home. It's an example of a dynamo. It converts mechanical energy to electrical energy. All right, it converts mechanical energy to electrical energy. It's a dynamo. All right. Okay. All right. So we are still talking about opposition to motion and that, and this eddy current is part of it. Okay, eddy current is part of it. Now, eddy current is an induced current circulating in circular disc or plate moving in a magnetic field. Okay, so eddy current actually happen not only in circular discs, so you can have them in rectangular discs, but it is an induced current that circulates in a plate that is placed in a magnetic field. And what it actually does is that it opposes the motion of the plates. A plate that is moving in a magnetic field, the eddy current will oppose that motion and make the plate to come to rest. So, simply put, it is an induced current that opposes the motion of a disc placed in a magnetic field. If you are able to understand that, eddy current is a current that opposes an induced current that opposes the motion of a disc placed in a magnetic field, it is done. So you can be asked in your physics objective that which of these explains eddy currents. So take note of that. Is that okay? So when a solid metallic sheet swings in a magnetic field, it courses through the magnetic flux of the field lines. This produces an induced EMF on the sheet or plate, which opposes the movement of the plate. Hence, the sheet will quickly come to rest and its motion is said to be damped. So eddy current has a damping effect. It stops the motion of a plate that is moving in a magnetic field. The induced EMF that brings about this effect produces the induced EMF that brings about this effect produces an induced current in the sheet. This induced current is known as eddy currents. Eddy current acts as a braking force because it slows down the movement and motion of a metallic plate in a magnetic field. This slowing down is called the damping effect of eddy currents. Okay? If the disc is replaced with a disc containing slits, right, the slits will increase the resistance of the disc and the eddy current is low, allowing it to turn in the magnetic field for a longer time. So the slit will reduce the resistance of the disc to the effect of eddy current, and because of that, the disc will turn for a longer time in the magnetic field. So guys, that is all about eddy current. Now we're going to look at the uses of eddy current and the advantages and disadvantages. Okay, some use of eddy current. One, they are used in damping of galvanometer to control the pointer movement in moving coil meter. So it is used to oppose the motion. So because of that, they use it in a galvanometer to control the movement of the pointer. They also use induction cookers or furnace for melting or furnace for melting large amount of precious metals, detecting invisible cracks in railroads which can endanger life. Then disadvantages of eddy current. Eddy current generates heat in the core of a transformer, armature of generators and electric motors. Okay, it causes loss of energy and power. It reduces efficiency of transformers, motors, and generators. Alright, so these are some of the uses and the disadvantages of eddy current. So guys, I think this is where we are stopping this class. I hope you have benefited a lot from this topic. I actually love this topic,
It's very interesting because whatever we discuss today, they are effects that we experience on a daily basis. Okay, so there are phenomena that we experience on a daily basis, and I really want you to as much as possible try as much as possible to understand this topic very well. Okay, so this was our topic for today. Before I leave, please subscribe to our channel, give us a like, give us a thumbs up, click on the notification bell so that whenever we upload a new video, YouTube will notify you. Okay, so thank you so much, guys. Invite your friends, help us to share these videos in your various social media platforms, and invite your friends to come and join and enjoy what you are enjoying. Reach us through the WhatsApp link that is under this video, or through the number that is showing on your screen with any issue that you have with physics. Thank you, and we hope to see you in our next class. Have a nice day.